My name is Timur. I am the presentation prep for Design Team 9. I'm going to get started and introduce our team members. This is Stevie Baldwin, our document prep, Alex Koshman, our team manager, Grace Jones, our lab coordinator, and Hautien Kao, our webmaster. We're going to be working on a robotic transportation vehicle this semester for Texas Instruments. I'm going to quickly go over the agenda, specifically the introduction and the design specifications asked of us from Texas Instruments. Stevie will then talk a little bit about the platform as well as how the RF control functions. Alex will then talk about interfacing and how the different components in our vehicle will communicate with each other. Grace will then give you guys an idea of the brushless DC motors as well as the wheels we decide to use for our project, and Hautien will then talk about some additional features that we plan on implementing given that we have enough time, as well as the budget and some risk analysis that comes along with our project. And finally, Alex will wrap it up with a summary. For the introduction, we'll be assembling and designing a robotic transportation vehicle prototype for Texas Instruments that they will be able to modify and use for their robotic and motor labs. This will involve communication between the central processor, which is a Stellaris Launchpad processor, and two microcontrollers, all of which have been supplied by Texas Instruments. We'll be incorporating brushless DC motors, which will drive and maneuver our vehicle. This was something that was specifically asked of us from Texas Instruments. We'll also be utilizing wireless RF control from our Kronos watch right here. This was also supplied from Texas Instruments. And finally, we'll design a battery-powered system to power our vehicle. We decided to tackle this towards the end of the semester once we've been able to make sure that our vehicle functions properly. We will then design a battery system to power our vehicle. Some design specifications. We first needed to find a suitable frame, which we just got in yesterday, that was durable, as well as one that will last for the entire semester, as well as one that will fit the dimensions for our microcontrollers. We're then going to replace the brush motors with brushless DC motors, as I had mentioned before, and Grace will talk a little bit about that coming up later in the slides. We'll use the two microcontrollers to control the motors, which will in turn rotate the wheels. The Stellaris board will perform as the central processor and will communicate with the microcontrollers. And we believe that developing this interface will be the most challenging part of our project and the most time-consuming, and so we set aside the most amount of time for that. Finally, we will incorporate the RF interface for user input control of our vehicle, which we will be using with our Kronos watch. This is a basic flowchart of our project here. As you can see, the Kronos watch will communicate to the Stellaris EVM directly. The Stellaris EVM will then command the microcontrollers to execute the programmable code which we'll be writing, which will then turn the brushless DC motors according to the programmable code, which will rotate the wheels, both the left front wheel as well as the right front wheel. I will now pass it over to Stevie, who will talk a little bit about the platform as well as the function of the RF control in the Stellaris watch, or the Kronos watch, sorry.
Thank you. Again, I'm Stevie Baldwin, and I am the doc prep for Team 9. I'll be talking about the platform as well as the RF controls for our design. For the platform, we decided to go with the Arduino robot platform. The dimensions of this is 200 millimeters by 170 millimeters by 105 millimeters. That's about 7.87 inches by 6.69 inches by 4.13 inches. The weight of our frame is 45 grams, but that's not including the boards and the motors we're going to add to it. So our final prototype is going to be way more than 45 grams. As far as what we're going to mount to our platform, we're going to mount two 8312 microcontroller boards, as well as one Stellaris board, as well as two motors. We decided to stack the motors on top of each other. The reason we decided to go with this layout is because our microcontrollers themselves are 5 inches by 5.5 inches. So we laid them out next to each other on the plate, it would actually overextend the plate. So we decided we're going to stack the boards and build a frame for it later to protect in case the vehicle were to tip over. As you can see, our kit comes in, our platform comes in pieces, so we're gonna have to assemble it ourselves. We're gonna use the RF control of our Chronos watch to control the movement of our vehicle. And to do this, we're gonna use a program called Code Composer Studio. Just a brief overview of what that is. It's a software that was developed and created by Texas Instruments. What it's gonna give us access to is all the libraries for the Texas Instruments family devices. So pretty much any board or device that TI comes out with, they download it to the software. The software also has applications for development, debugging, as well as compiling and simulation. This is good for us, and it's going to save us a great deal of time because we can program all of our boards and watch from the same program, compile at the same time. We're going to know exactly how it's going to run before we actually program the controller. This is going to be an advantage to us because we can, as far as avoiding situations where we might draw too much current or too much voltage into our boards, which is a big concern of ours. Hopefully we can catch it using the simulations before we actually plug our board into our board. Avoiding a situation where we might destroy our boards, which would be a costly and time efficient to send a new board out from Texas Instruments. This is the watch we're going to use to control our vehicle, and it will communicate with our Stellaris board, which is connected to our microcontroller, which will rotate our wheels. This will allow us to control the speed and direction of our platform. The watch comes apart and it is programmed using a USB port, which is good because USB ports are convenient and easy to use. Essentially, this watch will move our vehicle. How it works, it acts as a gyroscope. Based on the forward, backward, left, and right motions of the watch, it will track the X and Y values. And we, in turn, will use those values as variables to communicate with our Stellaris board. And based on the movement, it will move the robot in the direction that you tilt the watch. This is a screenshot of the output of the watch based on the forward, backward, left, and right movements of the tilt that the user inputs. And with that, I'm going to turn it over to Alex, who will discuss the interfacing of our boards.
All right, thanks, Stevie. Again, my name's Alex Cashman. I am the team manager, and I'll be going over the interfacing between the boards. We're going to be using Code Composer Studio, so we're going to be developing a program in C. So I'm going to go over the algorithm we're going to try and use. First of all, we're going to take the inputs from the watch as X and Y variables. When the watch is straight up and down, it's got a value of 0, and when it's upside down completely, it's got a value of 1. So from this chart, we're going to choose which direction it's going to be going in first. So the most important one is the center 0. We're going to have cutoff values, so even if you move the watch a little bit, the vehicle still won't move until it reaches that cutoff point. However, once you pass that cutoff point, say I want to go forward, you just lean it past that, and then it'll go to a maximum value. Here I've picked 0.25 and 0.5. Those values may change depending on experiments that we do and need to be developed later, but at this point they look like good values to pick. So from there, once we figure out which direction it's pointing in, we're going to do a simple equation to figure out what the RPM should be. Obviously 0 is simple, it's just going to be 0 RPMs. However, we're going to do, for each motor, say it's port A and port B, simple output of A and B as a function of X and Y. So each direction will have a simple equation. We're going to figure out the minimum value, which is going to be 0 once it reaches that cutoff point, and then a maximum. So you saw that 0.5 was a top value. I think the motors have a RPM maximum of about 4,000 RPMs, which is quite fast and will probably crash our vehicle. So we're going to make the equation to have a maximum RPM depending on what speed we want it to go. And that will be all included in that equation. From there, we're just going to output the RPM values from the microcontrollers out to the motors. So this is a picture of our Stellaris central controller, and this is one of the two 8312 EBM microcontrollers that will send the values directly to the motors. So from there, I'm going to hand it off to Grace, who will talk about the motors.
Thank you, Alex. As he said, I'm Grace Jones, and I'm the lab coordinator for Team 9. I'm talking about the motor assembly. So just a quick overview of the motor assembly. It's composed of two 8312s, as you heard before, two brushless DC motors, and 4 wheels, 2 of which are active and 2 of which are passive. The evaluation boards are composed of JTAG interfaces, which will allow us to debug those as well. As you can see from motor specifications. They're pretty powerful, have a rated voltage of 24 volts, a rated power of 55 watts, and a rated speed of 4,000 RPM. They're brushless motors, and we were told or asked to implement these instead of the current DC motors that they use for the motor lab because of the high efficiency that they have, the fact that there is no brushes connected to the stator and to the commutator to allow for less efficiency, and the fact that they operate as a synchronous machine, which would allow us to control it a little better. But however, the control is more complicated and the construction of it is more complicated, therefore it's more expensive. This is a functional diagram of the 8312s. As you see, it's a three-phase brushless DC motor. So the three phases are physically attached to the 8312s. And they send a feedback back to the motors, which use a Hall effect. And those are further connected to a DC bus, which goes down the line to connect to our M3 Cortex processor, that's where the signal is generated from to determine how fast the motors spin. This is the GUI, the graphical user interface control suite, where we integrated development environment developed by TI, but this is the interface here that we're using to control the speed of the motors, which is very important. We can't stress that enough because they are very powerful. When we're at a third of the power output, it spins incredibly fast. So we're using even less than that. And because of this, we have steering issues. So we will have to develop algorithm to better control these the steering, because in order for the device to move left or right, there should be a ratio speed between the wheels, and say we wanted to make a hard left turn, we would need to turn the right wheel completely on while turning the left wheel completely off, or yeah, that's okay. And that's just a big issue for us. And also the passive wheels should be omnidirectional, so we decided to use Mecanum wheels, which have rollers oriented 45 degrees on the circumference. It's a very clever design which allows it to move in any direction. And with that being said, I will hand it on to Hao-Tian, who will talk about the budget.
Okay, thanks, Grace. My name is Hao-Tian. I'm the webmaster of Team 9. Here is our budget. We have $500 budget, so we spent $50 for our platform and $18 for our wheels and $30 for our battery. And the BLDC motor is an optional part because TI has provided two powerful motors, so we don't have to buy that. So the remaining is going to be $317. So we can add some additional features for our robot. So the first one is we are going to build a self-driving control robot. TI have provided our code for the self-driving control, so it is easy for us to build a robot with a self-driving control. And we can also build some sensors in the robot, like the infrared and ultrasonic sensors, so the robot can detect the object around the robot. And we can also paint our frame, or we can build a cover for our robot, and some LED lighting for visual appearance. And we can also use a wireless camera to in front of our robot, so we can control the robot with a watch and see what is in front of our robot with an iPhone or a laptop. And here are some risks that we need to be considered. The first is the power supply issue, because we are using a 24-volt battery. So we have to figure out our battery have enough lifetime for to supply our robot, and we need to give enough power to our robot. The coding and the interfacing is very important to our robot because we have several paths to program. We need to program our watch. We need to program the launch pad and also the microcontrollers. So we have to make sure they are working correctly and communicate with each other efficiently and effectively. And we are using this watch to control our robot, so we have to make sure the watch and the receiver is working in the correct range, so the receiver can get the signal from our watch. And also we have two powerful motors. The max speed is going to be 4,000 RPM, so it might damage our frame during the testing. So we have to find a reliable frame for our robot. And the last thing is temperature issue, because the board and the BLDC motors is working under the 24 volt, and the current is going to be very high, so the temperature might be very hot. So we have to make sure all the equipment is working under the right temperature, and we also maybe we can build a cooling system for our robot. So I'm going to pass it to Alex for summary.
Alright, so a quick overview of what we presented today. Texas Instruments has tasked us with building a robotic transportation vehicle for their motor lab. And they asked us to integrate this Chronos watch as well as the microcontrollers they've supplied to us. We also need to develop some code to communicate between those boards. We also would like to add some additional features if we have time at the end when we're done with everything else that we've been required to do. So first off, we went over the platform, why we decided to get that one, and what some of the strengths of it are. We went over the RF control and the watch, how the watch is going to work, the interfacing and what our algorithms and planning was for that. Some of our motor options, why we went with brushless DC, and what also our wheel options were. We went over a list of additional features that we would like to add once we're done. Then we went over the budget and saw how much money we have left over in case something goes wrong or we want to add extra things. And then finally, we went over some of the major risks to our project. So here's a list of our references. Does anyone have any questions?
The car that you have to move, how much does that weigh? Do you have an idea, or?
It depends a lot on.
Well, the actual platform is 45 grams, but it's going to be, that it doesn't take into account how big the motors are as well as the
Right.
microcontrollers.
Because I'm thinking you said each motor was 55 watts apiece, 110 watts for 45 grams.
Yeah,
Yes,
those-
that's a big problem.
Yeah.
You're going to have to add like counterweights to our vehicle or like. you know,
Or
very-
downsize the motor, is that a possibility?
That was what
Yeah,
we also, I'm sorry. That was something we also included in our budget, $100 for additional motors, because the ones that we currently have are pretty powerful. We're going to try to work with them, but we might have to switch those out.
All right, thanks. Any other questions?
Is there going to be a variable speed to it, or like you said with the tilt sensor, it seemed like there was just on and off?
Yeah, so that equation that we're going to do, once it reaches the point, it's going to linearly increase according to our equation until it reaches the maximum value. So it's going to start ramping up after it reaches that peak and increase linearly if we can until we get to the edge.
So you're going to have to tilt it all the way upside down?
We can set the values because remember how there's like a cutoff point for it to move? We're going to have a maximum value as well, and after that, it just goes at its maximum speed. Anyone else?
All right. Okay, so I guess just one team today, there's no team 10? No? Okay. So yeah, just hand out your evaluation sheets on the way out, and I'll be in the lab again if you want sign-offs on lab 4. If not, I'll see you on Friday.